Alright, we're back. This is Sparks AP Calculus, and we are on day 45, solving optimization problems. So this right here is just a general tips or approach to go through when solving optimization problems. And sometimes these can be rather difficult, so having a list of things to try is helpful. So one of the first things would be determine the quantity that has to be maximized or minimized. That'll be the first thing. 2. Sketch a picture. And identifying all the variables or quantities that do not have a value. Write a primary equation, area, volume, whatever it is that if you're trying to max or min, you're probably going to have an equation to go with it. So write a primary equation that represents the quantity to be optimized. And you need to be aware that they have more than one variable. Which leads us right into number 4. If there is more than one variable in the primary, you might have to write a second equation. Which becomes a system of equations. So you're probably going to have to solve for one variable and stick it in the other. And once we have the equations, we're no longer dealing with the word problem. Well, how do we find maximum and minimums? Take the derivative. And just like we checked to find out if that particle is turning around in the last video, we're going to use sign analysis to verify max and mins. Because if we're looking for a maximum, we don't want to just find the places where it could be a max or it could be a min. If you just write it down, maybe it was actually a minimum. So you should check and see which ones really are the maximums or minimums. We'll put BB without an example. So we're talking about a manufacturer wants to design an open box. That means it does not have a lid, having a square base and a surface area of 108 inches. And we're trying to maximize the volume. So this is what we're looking for. So what would be the primary? That would be, well, let's see. Let's try and draw a picture. Right. Something like that. So we want to maximize the volume. So we know it has a square base, so we could call the base x, and then the height y, and then the volume is going to be x squared y. And our volume equation has 2 variables in it, so we need to find a way to relate them to each other. And we can do that by finding the surface area, which is 108 square inches. And so each one of these faces here are all going to be xy. And there are 4. 1, 2, and that one over there, 3, 4. So the surface area is going to be equal to 4xy, and then we have to count the bottom. And that one is a square, and it is x squared. So this is how we relate the two of them together, and we know that that is equal to 108. So we need to either solve for x or solve for y and plug it in the other equation. So let's solve for y. Divide by 4 x's. So we have y equals 108 minus x squared over 4x. And this we're going to plug in right there. So here's our messy volume now. So the volume is equal to x squared times y, which was 108 minus x squared all over 4x. And this is what we need to find the derivative of. We definitely want to simplify this. Let's see, let's get rid of that. And then distribute. So we're going to have 108x minus x cubed. This is over 4, which is 27x minus 1/4 x. Oh, this is x cubed. And this is volume, so we need to find v prime. Because if the derivative is equal to 0, that's where our potential max and mins are. Set that equal to 0. Solve for x. I'm going to add 3/4 x squared to both sides. Keep everything positive. So we get x squared is equal to 9 times 4, 36. So x is equal to plus or minus 6, but since this is the real world problem, we're going to throw out the negative. So this is a possible max or min. So let's test it. 0, 6, we know the slope is 0. Who knows where it ends? That's, something big like that. Alright, so if we plug into our original function, if we get 0, it's 0. If we plug in something in between, get positive, something bigger than 6, we're gonna get something negative, which means this has to be a maximum because the slope goes up, flattens out, and the slope goes down. So our answer, volume is maximized at x equals 6 because v prime changes from positive to negative. And what is that volume? 6 by 6 by 3 gives us 108 inches cubed. Alright, another box from a rectangular piece of cardboard. So what is it we're trying to do? We're trying to hold the most amount of soup. So we're trying to maximize volume again. So we're going to need the volume. And we're starting with a rectangular piece of cardboard that is 25 by 40. And I'm going to cut a square from each corner. We don't know what that is, but we're trying to figure out what that would be to maximize the volume. So this would be x, all the way around there. And then we fold up the sides. We get something like that. And this is the height of x. We just need to figure out what the side lengths will be. So our base is basically going to be this distance right here. So it's going to be 25, this one's going to be 25 minus 2x's, and this height here is going to be 40 minus 2x's. So our volume then is going to be the height, which was x, and the base, 25 minus 2x, and the height, 40 minus 2x, and this is what we're going to want to take the derivative of. I wouldn't mess around with the product rule. I would go ahead and multiply this whole thing out and then find the derivative. So why don't you go get started on that, pause it now, and see if you come up with the same answer I do. Alright, I got 5 and 50 over 3, and I checked it with the sign chart, and I got a maximum at x equals 5. Go ahead and try example 3 on your own and check your answer. Alright, you can see my picture. I add a little color so you can figure out there's a lot of things going on there. But I end up with the dimensions being 6 by 9. So I'm going to skip example 4. I'm going to give that to you guys to work out. And I'm going to go to example 5. So we're going to talk about minimizing the surface area of this solid that is formed by adjoining two hemispheres to the ends of a right circular cylinder. Okay, so we're going to minimize surface area. That's what we're going to do. And bear with me as I try and draw a picture. Alright, so there's my right cylinder. And then I'm going to have look through there, there's a half of a ball on top of it. The same thing down here on the bottom. So the surface area of this, let's see. Surface area of this sphere is going to be 4 pi r squared, and the surface area of the cylinder is going to be the area of the base. No, not the area. The circumference of the base, which is 2 pi r times the height. So there's our surface area. We add those two together. Surface area equals 4 pi r squared plus 2 pi r times the height. We got too many variables in there, but we do know that the volume, let's see, volume of a sphere, 4/3 pi r cubed, plus the surface area, which is the area of the cylinder, which is pi r squared times h. Oh, sorry, that would be the volume of the surface area. So now we have those two equations, and we need to put them together. Looks like fun. So one of the questions is, do you solve for r or do you solve for h? I'm going to solve this for h because we're trying to minimize the surface area with respect to the radius. So for the sake of time, I'm going to go ahead and simplify this. So you might want to pause it so you can do it as well. Alright, I end up with h equals 36 minus 4 pi r cubed all over 3 pi r squared. And we're going to plug that up here for this h. So, put this over here. We're going to have surface area is equal to 4 pi r squared plus 2 pi r times the h I just found. Alright, so we're going to have to do some manipulation, and in the interest of time, I'm going to pause this to do that. A little messy, but I ended up with this. Area equals surface area equals 4/3 pi r squared plus 24r to the negative 1. And we need to find SA prime. So go ahead and pause it and do that right now. And we need to set that equal to 0. So now we're going to solve this, and I'm going to pause it again. Alright, another little bit of a mess, but I end up with r equals the cube root of 9 pi. And then we're going to need to do a sign chart and verify that that really does minimize our surface area. In order to figure out what interval we should use, you might want to plug in 9 pi and take the cube root. But the cube root of 8 would be 2. Cube root of 1. So it's got to be somewhere. Oh, that should be divided by, huh? Sorry. That is 9 divided by pi. That makes a little more sense. So I'm going to choose the interval 1, 2, and then right in here we've got cube root of 9 over pi. Sorry about that. And then when you test it, find out it's positive negative, you end up with a negative and a positive, which means this is a minimum. Alright, this is the end of this video, and I'm going to expect you guys to do some of those other examples. See you next time!